Aloha and welcome to my talk. Today we're going to be talking about macOS stealers. My name is Patrick Wardle. You might know me from the Objective-See Foundation, the organizer of the Objective-See conference, also the author of the Mac malware analysis books, and most recently the co-founder of W. It's a new venture. We're building components to be integrated into Mac security products. All right, but let's dive into the topic today, and I always like to start my talks focusing on what I hope you will learn today. So this talk is all about macOS info stealers, and we're going to focus on analyzing some of them, which will then give us the understanding to build what I hope are generic detections and protection mechanisms. As we see on the slide, we'll also touch on some topics of reverse engineering, programming, and more. So, what are stealers, info stealers? Sure, many of you already know this. To make sure we are on the same page, though, a brief slide kind of introducing them. I like to think of them as a subset of malware. And what makes them kind of a subset is they really only have a small number of capabilities and really one goal, which is really to collect and exfiltrate, steal all the things, hence their name. A few other interesting things about them that, in my opinion, differentiate them from other malware is the fact that they spread opportunistically and indiscriminately. They're generally not used in targeted attacks. They also run once. They rarely, if ever, persist, which is unusual because most other Mac malware will persist so it can maintain access on a box. And then finally, it's kind of all about money. These stealers are generally about financial gain. So in some ways, there's a lot of overlaps with adware, and as we'll see, these stealers are eclipsing adware in terms of prevalence, and in some cases, it's like stealers are the new adware for macOS. So what do they steal? On the previous slide, I said they steal all the things. Well, it's a little more nuanced than that. And specifically, they steal things related to generally accounts and access. So there's a great write-up by Phil Stokes, Sentinel-1 researcher, who's done a great amount of work on macOS stealers. I cite him several times in this presentation. And he articulated basically the main categories that stealers are interested in. And these include things like session cookies to give the attackers access to the victim's accounts. Generally also accessing or collecting the user's password. This is mostly so that they can then unlock the macOS keychain, which holds all the things, passwords, auth tokens, certificates. They're also generally interested in browser data, so we'll see them going after autofills, browser passwords, credit card stuff, et cetera, and then also cryptocurrency wallets, especially those that are browser-based or use browser-based extensions. Now, it's a valid question, why do we care? I mean, yes, we do care dearly about our users, and when their cryptocurrency gets stolen, we all shed a tear. But more than that, these stealers are actually growing into a larger problem that's impacting even those in the enterprise. And we like to talk about trends a lot. This is actually something that I think is relatively new for 2023 and definitely in 2024. And this is the kind of greater impact of stealers, because stealers have been around for a while. So we can see some news headlines. The attack, though, that I like to focus on is the Snowflake data breach. And Snowflake is a large company that hosts other companies' data, and all the customers of Snowflake, AT&T, Ticketmaster, Santander Bank, all their information was getting stolen. Everyone was like, did Snowflake get hacked? Well, what turned out is that hackers basically had credentials for each of these customers, and then were able to access all the data that was on Snowflake's cloud. And again, this was generally attributed to stealers being the source of the credentials. Now, we also need to care because stealers are becoming ever more prolific. There's a great article by Lily at Wired, very well researched, and in this, she notes that, again, info stealers have been around for a while, but now they're becoming ever more prolific. And adversaries are really seeing the value of them, especially to supplement or as a precursor to other attacks. So as mentioned, in some cases, we're seeing now stealers being the most prevalent threats to macOS users. So that's a brief overview. What I want to now do is dive into the most prolific, one of the most well-known stealers on macOS, known as Atomic, or Amos by its authors, because it's a great case study that illustrates exactly how these stealers work, how they infect Mac users, what information they're after, all the things. So this specific stealer was discovered in 2023, so pretty recent. But since then, it has jumped to the top of the charts by some metrics of being the #1 most prevalent threat targeting macOS users. And that's actually very impressive because for the last decade plus, this has always been adware. You know, Pirate, Genio, some annoying adware has always kind of been at the top. So to see stealers kind of even make it to this chart and then hit #1, in my opinion, is impressive. So kudos to the malware authors. But also, I think as defenders, this is important for us to understand, especially when we talk about defense. So you might be wondering, how does this malware, which is so prolific, spread? And the question to that is a little nuanced because the way Atomic Stealer is created is it's written by an individual developer or perhaps group of developers and then is offered as a malware as a service, which basically means that the creator will rent it out or sell it to other crimeware actors. And as we can see, the quote on the slide then shows that these actors are responsible for infecting Mac users. This makes a lot of sense. This allows people who are good at targeting victims to do their thing, whereas the software developer, the malware developer who's good at writing code can focus on that. Most common, though, we see them, the actors that buy Atomic Stealer are basically trying to coerce the user into downloading fake applications. And so let's look at some examples of that. One example is sponsored ads. This is a very common technique. The actors basically somehow get a Google ad to be displayed for a common application. A naive user will then inadvertently click on that link. We've also seen cases where the adversaries will clone a legitimate website, like Homebrew, and just mirror it, and then the download link will point not to Homebrew, but to the malware. The main takeaway is, regardless of these approaches, the user is the one who has to be tricked into both downloading and running the malware. So it's very high touch and requires a lot of user interaction, right? So we're not seeing 0 days, we're not seeing supply chain attacks. It's like the basics. So you might be wondering, rightfully so, if the user has to be so involved, don't things like Gatekeeper, which are built into macOS, specifically to prevent the users from essentially infecting themselves, come into play? And the answer is yes, but what the attackers generally do is provide instructions to the potential victims about how to sidestep this or bypass. Now, this isn't like a Gatekeeper exploit. This isn't even a Gatekeeper bypass. It's just like sidestepping. So up to macOS 15, if you right-clicked on a non-notarized or untrusted application or program and clicked open, macOS would actually allow you to open it. Whereas if you just double-clicked it, macOS would be like, yo, no, I'm not running this. So we can see some examples on the slide where the disk image, which contains the malware, also contains the instructions to get the user to sidestep macOS's built-in mechanisms. Okay, let's talk about capabilities. As I mentioned, the goal of stealers is just to steal stuff, right? This is not rocket science. And so basically what they do is they gather, collect as much information as they can, and then exfiltrate that, and they are done. So if we look at embedded strings of the Atomic Stealer, we can get a really good sense about what it does. So we can see strings related to the user's password, the keychain, browser data, crypto wallets, and then we also see the address of the normally what would be the command and control server, but in this case, it's just an exfiltration server. If we load it in a disassembler, we can see all the method names, which are hopefully very descriptive. In initial versions, there's no obfuscation, so as malware analysts, this makes our job very, very trivial. And if we hop over to the main function, we can see they're just called right away. So again, really not that sophisticated. First, though, let's talk about the anti-analysis logic, because as many of you are likely aware of, if you're analyzing a malware sample and it has anti-analysis logic, that is the thing you want to both identify and bypass first. Otherwise, your continued analysis might be complicated or thwarted. So if we look at Atomic Stealer, we find that it implements some pretty basic anti-analysis logic. Specifically, it looks to figure out if it's running in a virtual machine, and if it is, it will exit. The malware authors are making the fairly accurate assumption that if the malware finds itself running in a virtual machine, it's probably being analyzed by someone like myself, so it should exit to prevent, or at least attempt to prevent, continued analysis. So what does it do if we disassemble it? We can see they're executing macOS's system profiler utility. That will give some information about the machine, including potential strings if it's running on a virtual machine. You can see it's checking for both VMware and Apple virtual machine. And if it finds either of those, it'll exit with 1B hex or 27 decimal. So if we pop into a virtual machine and we run this system profiler utility ourselves, we can see that, yes, indeed, there is a model name which contains a string related to virtualization because we are in a virtual machine. Which then means if we run the malware in a debugger, because it has this anti-VM detection, it will detect that same string, say, yep, I'm in a virtual machine, and then exit with that error code we mentioned. So the question is, how do we bypass this? Super trivial. You just knock out the call to executing that utility, or in a debugger, you just step over it. So really not that complicated once you have pinpointed that. And then your continued analysis can continue even within a virtual machine. Okay, let's now get back to the capabilities. Stealers are generally most interested on macOS about the user's keychain because that has passwords, credentials, authentication tokens, a lot of very interesting things. So if we look at the atomic stealer, we can see that first it does in a do-while loop is to get the user's password. And I'll show you on the next slide how they do that. It's pretty straightforward. But the key is they need the user's login password to unlock the keychain. And then once you have the user's password, it's trivial to dump the keychain. Basically, you just execute a utility. In this case, they've packaged up a precompiled Python utility that is designed to dump the macOS keychain. And if we look at a process monitor, we can see they drop and execute it. Here it's called Unix1, and they pass the path to the user's login keychain, and then also the password that they obtained. And then from that, they can dump the keychain and exfiltrate that. So how do they get the user's password? Super basic. I hope you're seeing a trend here. Most of these stealers are really not that sophisticated. So what they do is they simply use AppleScript to masquerade as a system preferences alert or pop-up saying, yo, I need your password. And this just like appears when, the malware is run. And so like for any of us, we'd be like, okay, this is weird. I'm not just going to give it the password. But apparently for the average user, maybe this works. And again, they do this in a do loop. So if the user clicks cancel, it'll just keep popping up. So again, really not that sophisticated, but apparently sufficient. One interesting thing, to validate the password, they then invoke macOS's DSCL utility, which can tell you if a username and password combo are valid. So again, in our trusty process monitor, we can see the malware executing that to validate that the password the user entered into this fake profile is indeed the accurate or correct one. Okay, so now they have the password, they can unlock the keychain, but then they can also access a lot of browser data. And so the Atomic Stealer focuses on a wide variety of browsers. They don't mention Safari specifically, but my understanding is a lot of Safari information is in the keychain. So if you're dumping the keychain, you'll get that information as well. Again, the method names are super descriptive, so we can see one like grab Chromium. And if we look in a disassembler for cross-references to strings that are found within that function, we can see paths associated with, for example, the cookie file, passwords, web data, autofill that Chrome and other Chromium browsers will use. There's also embedded strings that are related to common cryptocurrency wallets, specifically browser extensions. So again, the malware will see if those are present and grab those if it finds those. All right, let's now talk about other macOS stealers. And there's a large list of these. These are mostly from 2023 and 2024. Now, when I was creating the slides to give this presentation, I said, okay, we're going to do a case study on Atomic Stealer, and then we're going to dive into all the rest of the stealers to show all their differences and how unique and amazing they are. Guess what? They are all exactly the same. I mean, likely not written by the same creator, but like once you've looked at one stealer, generally speaking, you've seen them all. Now, there was a talk this morning that dove into one of the more sophisticated ones, so they're definitely out there. But again, generally speaking, at least the ones I've listed here, which are very prevalent and common on macOS, almost identical to the atomic stealer, meaning they require user interaction to infect a system. You have to bypass gatekeeper. They basically always ask for the user password. None of them, except for the top one, persist. They grab the keychain, browser data, and exfiltrate it. So I was like, you know what? I'm not going to bore you all with the same details. What I want to now talk about is how we can generically thwart these ever more prolific and ever more impactful threats. So let's start with some thoughts on detection. Now, I've been a huge fan of detecting malware with persistence. In the context of this presentation, when I say persistence, I'm talking about how malware installs itself so that it is automatically re-executed every time the box is either rebooted or the user re-logs in. And this is essential because if malware doesn't persist and you reboot the system, well, you've basically just disinfected the system. Guess what? Stealers don't care. They only have one thing to do, which is grab and exfiltrate all your data so they don't persist. So that was kind of a bummer. And I wanted to mention that I've been a big fan of persistence for a long time. The first talk I gave 10 years ago at Virus Bulletin was about persistence, because back then, all Mac malware persisted. So stealers, though, don't. So we have to think different and figure out some maybe new approaches to generically thwart them. So I want to talk about some of the ideas, specifically focusing on detecting items that have problematic or non-existing code signing. Items, programs that access sensitive files that aren't authorized, and then finally also unauthorized network access. And the reason these three approaches work really well for stealers are because most stealers are A, not notarized, and B and C are then going to access, for example, browser cookies, which is weird if they're not a browser or a trusted system component, and then access the network as well. So if we can programmatically monitor and detect this activity, in theory, we should be able to generically detect and thwart basically all the stealers. So let's look at that a little closer. First, let's talk about the detection via gatekeeper override. So I mentioned that all the stealers I've seen and that I'm aware of are not notarized. And that basically means when the user double-clicks it, macOS is going to be like, yo, I'm not going to run this even if you're trying to, unless the user right-clicks on it, clicks allow. On macOS 15, there's a few more hoops you have to jump through, but there's still a way for a user to essentially approve a program to be run that's not notarized. And there's maybe some legit cases, perhaps some third-party developer doesn't want to notarize their code and their users want to run it, but generally speaking, malware is not notarized where legitimate software is. So as of macOS 15, there is a new event you can register for that will be delivered to your detection program if the user goes ahead and bypasses or sidesteps Gatekeeper. So let's look at how to do that. So the majority of the detection approaches we're going to briefly discuss today are going to make use of Apple's endpoint security framework. Now, this could be a whole talk unto itself. In a nutshell, this is a framework that Apple provides that if you are writing third-party security tools, you can specify events of interest. You can register yourself then to the operating system, and then when these events occur anywhere on the system, macOS will invoke your code to either A, notify you, or B, actually allow you to authorize the event. So let's start with the Gatekeeper user override event. This is a notification, means we can't block it, but at least we will get notified. Now, don't worry about all the details of the code. It's largely up here as a resource. But in a nutshell, we specify the event of interest. We create what is known as an endpoint security client. We then specify a handler for the event and then subscribe. Once we have executed this, every time a user bypasses Gatekeeper, we will now get an alert. A little bit more information. There's a structure that then gets delivered to us when this event occurs. Again, don't worry about all the specifics, but it provides information like the path of the item that the user just allowed to execute, and it's code signing information. So at the bottom of the screen, I've compiled this code, and I've run it, and we can now see that when I right-click on a sample of the atomic stealer, the Gatekeeper would normally block, allow it to execute, woohoo, I get a notification basically saying, yo, unauthorized item was executed. So that's good. The problem is, though, again, that's only a notification event. So the damage is probably already done. The stealers quickly ran, grabbed all the things, exfiltrated it, game over. So I want to focus more on blocking unauthorized activity, which you can do with the auth-exec event. And the idea is you can register for a authorization event, and then for any new process that is spawned, the operating system will intercept that, pause it, and then come and ask you, yo, should I allow this process? And you can actually then instruct the operating system to either authorize and allow it or deny it. And if you deny it, it will actually block the program from executing. So that's super, super powerful. Really thanks to Apple for giving us these capabilities that we can do in user mode. So again, the code is pretty straightforward. It's just like the gatekeeper override. We register a client. We specify the event of interest. In this case, it's an auth exec. And then we subscribe to that. So now we are getting a callback anytime a new process is launched. How do we determine if it's good or bad? That also could be an entire presentation. For now, we're just going to check if it's notarized or not. Notarization basically means that the item has been submitted to Apple. Apple has performed some static, perhaps dynamic analysis, and come to the conclusion that it is not malicious. Apple has inadvertently, very, very occasionally notarized malware, but 99 out of 100 times, Apple does not. And malware authors also don't want to give their binary to Apple before they deploy it. So the vast, vast majority of malware is not notarized, where the vast majority of legitimate software is. It's going to be a little bit more nuanced, but that generally holds. And with stealers, it's even more clear-cut, because a lot of them are malware as a service, so the developers don't worry about notarizing it, and then the people who are deploying it are just really focusing more on tricking the users into running it directly. So TLDR, vast majority, all the stealers I've seen are not notarized. So since we have a process authentication event for a new process, how do we check if it's notarized? Turned out it's pretty easy. Again, don't worry about the code too much unless you're really into these things. But the idea is there are code signing APIs that macOS exports or exposes to us that we can query and say, hey, a given process or a given path, is it notarized? And the code signing frameworks will then say yes or no. So now we have an answer to determine if an item is notarized or not. If we find a non-notarized item, we should probably block that. And we can do that by just returning a deny constant to the endpoint security framework, which will then prevent that binary, that process, from being executed. So if we implement that, here's a very simple test. At the top, I run some legitimate software. This is GitHub Desktop. It's signed. It's notarized. We still get the process auth event. Again, this is given to us for every single process. We quickly check to see if it's notarized or not. This is very efficient, done by, again, Apple's code signing APIs. Comes back and says, yes, this is notarized. OK, that process is allowed. In the case of malware, specifically stealers, we can see that it's not notarized. So in this case, we block it. Now, this is a very powerful heuristic that you can extend as well. The fact that now you are getting an authorization request from the operating system anytime a new process is about to start means you could do way more things than just check if it's notarized or not, right? You could run Yara signatures. You could see all sorts of things. But for now, we're just focusing on notarization. Next, I want to talk about blocking unauthorized file access, because this is really the meat and potatoes of stealers. And if you think about it, who should be accessing cookie files? The browser and, sure, maybe some trusted system components that are doing some indexing. But random card trading app downloaded from the internet? Yeah, probably not. So what we can do is take that concept and basically build a very powerful file monitor, essentially, that will monitor files we choose and then validate who is accessing them. So again, we use Apple's endpoint security. In this case, we're going to use a auth open event, which the operating system will deliver to us for any file that is opened. What we're going to do, though, is we don't care about most files on the system. We just care about select ones. This might be the user's document directory, their desktop, or browser subdirectories that contain autofill data, et cetera, et cetera. So there's one important concept to grasp here, and that is mute inversion. OK, so when Endpoint Security Framework was developed, Apple introduced the concept of muting. So imagine you're building a file monitor, and you don't want to monitor like every single process. You want to ignore, for example, Spotlight, which is always indexing things in the background. You're like, that's annoying. So Apple said, okay, cool, we will give you muting APIs that you can say, ignore a process or a path. And that was all well and good, but there was no way then to flip that on its head and say, you know what, I actually just want to focus on one process or one directory and ignore everyone else. So recently what Apple added was this concept of mute inversion. And on the slide you can see we invoke the ES-invert muting API. This basically tells the endpoint security framework that we are doing the opposite, and instead of caring about everybody and then muting one or two things, we're actually going to do the opposite, which says ignore everyone. And then when we invoke the mute API, since it's inverted, this tells the endpoint security framework that we are interested in either just one specific process or one specific location. And you can call that multiple times if you have 3 or 4 files. But again, the takeaway is now you can build essentially a file authorization monitor for either specific processes or, in this case, specific file locations. So what we do here is we create that. We're basically monitoring, in this case, I believe it's, yes, the user's document directory. Again, this could be the browser directory or a specific file. And with our file authorization utility now up and running, whenever any process attempts to access any content in the documents directory, the operating system intercepts that, asks us if we're okay with it. We can examine the process that's trying to access the file, and if we deny that, the operating system will block that for us. So very easy in this case. We could check if it's not a trusted application or something that's been approved. In the case of stealers, this now gives us a fairly generic capability to block the things. The last detection I'm going to talk about is network detection, because this is, again, something very common to all stealers, which is once they've collected the data, well, it's really no use until they get it to an attacker. So if we create a network monitor, this is, again, a very powerful way to generically thwart stealers and also other malware. So the example I have actually on the slide goes back to the 3CX attack. I talked about this last year. It's not stealer specific, but what it illustrates is if you have a network monitor in place, regardless of the malware, now you have a very powerful capability to say, hey, this is a new process or something I've never seen before. Why is it talking to endpoint XYZ? Or why is it trying to resolve some strange domain? This really works well for stealers, right? You can say, oh, the process that's trying to access the network is not notarized or was executed because the user bypassed gatekeeper and block it. And again, this extends to other malware detection as well. All right, so let's wrap this up. I know lunch is around the corner and we are all very hungry. Takeaways. Stealers becoming super prevalent. I was very impressed that they seeded malware or adware and now really hold the #1 spot in terms of widespread threats targeting macOS. Their impact is also something that we shouldn't underestimate, and I'm guilty of this myself. I was like, okay, they're just stealing from crypto bros and who cares? But we're actually seeing, especially in 2024, that they are becoming the precursors to more problematic attacks. For example, ransomware or larger data breaches, especially in the context of the enterprise. And then lastly, the complexity, really not quite there yet. The atomic malware stealer that we talked about, it's really not that sophisticated, but it's still very widespread and has an impact. What will cause these malware specimens to evolve are two things. One is we become more aware and write better detection capabilities as third-party defenders. That will definitely cause a change. Also, though, Apple is introducing additional security features, especially in macOS 15. For example, the gatekeeper bypass is now way more problematic. So we're going to likely see the attackers have to evolve. Let's keep an eye on these stealers because it's very likely that the next generation is going to be more sophisticated. So my goal today was hopefully show you a good understanding of stealers, dive into specific ones, and then with an understanding of those, hopefully inspire all of us to build better heuristic-based detections that can generically thwart both the stealers of today and hopefully the ones of tomorrow. Now, if you're interested in learning more about this, I've written the book on Mac malware analysis. Volume 1 is free online, so this is not a sales pitch. And I'm also excited to announce that Volume 2, which focuses on programmatic detection, kind of the second half of this presentation, is about to be published. I have the final manuscript due on Monday, so I know what I'm going to do this weekend. I'm going to drink Guinness and make my editor happy. That should be published in January or February. And like the first version as well, it's going to be free online. The hard copy is you can buy it, but all the royalties from that go back to the nonprofit Objective-See Foundation. So that's kind of cool. And lastly, speaking of the foundation, I just want to take a second to thank the companies and the products that support our foundation. I see many of you here from companies that work for these companies, so thank you. This allows us to host the Objective by the Sea Foundation, publish free books, do student training, scholarships, all sorts of amazing things. So thanks to them. Also, I want to thank you all for attending my talk. Really appreciate that. And thank you to Karen, Allison, the VB crew. I always show up like 10 minutes before my talk, and I know I stress them out. So, I want to thank them for their patience and for hosting me every year. So, again, thank you for your attendance. If there's any questions, I can answer those now. If you're all hungry and want to bolt, that's fine too. I will be around. But that's a wrap. Thanks again.